So in this section, we'll be looking at how to apply the derivative of a function to derive a result known as the mean value theorem, our topic for 3.3. So here we'll look at some intuition for us to make sense of the mean value theorem, our eventual result that we'll get to in a couple slides. So suppose we have a car that's driving between some time intervals t1 and t2. So since our car is always going to be at some position on the highway, it is assured that the function for the position, let's call it x of t, will always be continuous over the time interval. In addition, since the car will always have a speed registered on the speedometer, the car will always have an instantaneous velocity v of t. Since velocity, as we've discussed in Unit 2, is the derivative of x of t, this guarantees that x of t is differentiable over the entire time interval. So let's suppose some additional constraints that we note the car traveled 60 miles in an hour, indicating to us that its average speed or average velocity over the time interval was, well, 60 miles per hour. So 60 miles per hour, knowing the average speed was 60 miles per hour does not tell us anything about the instantaneous velocity at any specific point except for one thing, which is that we know the instantaneous velocity had to be equal to 60 miles per hour at some point on that time interval of the trip. So it is guaranteed the instantaneous velocity at some time t equals c on a time interval must be equal to the average velocity of the trip, 60 miles per hour. Why is this so? Let's take a look at some different cases. If the car is on cruise control at 60 miles per hour for the entirety of the time interval, that means its instantaneous velocity was always 60 miles per hour. But what if this wasn't the case? What if the car was first moving faster, 60 miles per hour, and then at some point decided to move slower than 60 miles per hour? Well, if the car is moving faster than 60 miles per hour at one point, then that guarantees that then at another point the car is going slower than 60 miles per hour. That guarantees that the car had to be moving 60 miles per hour at some point. Likewise, if we run the situation reverse, if the car is initially moving slower than 60 miles per hour at one point, and then at another point the car was going faster than 60 miles per hour, the car had to be moving at 60 miles per hour at some point. So regardless of the situation, we can see that there always had to be some time where our instant velocity t was equal to the average velocity over the time interval. So one can make the following statement based off of this. In terms of calculus, so you could say if the car at the point is at a point on the road at all times over the interval, i.e. x of t is continuous, and has a velocity at each point, i.e. x of t is differentiable, then at some point t equals c on the open interval, t1 to t2, the instantaneous velocity of the car must have been equal to the average velocity 60 miles per hour, aka there must have been a point where the speedometer on the car read 60 miles per hour. In terms of calculus, what we can say is that v of c equals our first derivative of position function must have been equal to 60 miles per hour at some point on the trip for our car. If we extend this to more generally a function, this gives us a result known as the mean value theorem, or MVT for short. It states that if a function f is continuous on a closed interval a to b and differentiable in the open interval a to b, then there is a value c for c between a and b guaranteed such that the instantaneous rate of change of f is equal to the average rate of change of f over said interval. So here we've replaced our position function x with f, and then we are now applying, we're now equating the instantaneous rate of change, aka what would be usually velocity, instantaneous velocity, with the average rate of change, the average velocity over an interval. So we're guaranteed that f prime of c, in terms of notation, must be equal to the average rate of change of f over the interval a to b. All right, note that in order for the mean value theorem to apply, two key conditions must be met, and these are the key conditions that you must check, is that f must be continuous on the closed interval a to b, and f must be differentiable on the open interval a to b. So if we look at an example right here, we can see that this is a graph of some function f right here. F is continuous over the entirety of its domain, but we can't apply the mean value theorem here because we can see that there are cusps and corners where our function is not differentiable at. If we had decided to apply the mean value theorem over an interval from negative infinity to 0, we'd be perfectly fine, as there are no cusp and corners over this specific interval. But if we were to apply the mean value theorem from, let's say, negative 3 to 5, we would not be able to apply the mean value theorem because we do have cusps and corners over this interval, points where a function is not differentiable at. In terms of a geometric interpretation, the mean value theorem right here guarantees that at some point C for a continuous and differentiable function over an interval, that the slope of the tangent line will be equal to the slope of the secant line over the interval of interest. Again, the slope of the tangent line being our instantaneous rate of change and the slope of our secant line being our average rate of change. So according to mean value theorem, if a function is continuous and differentiable over a certain interval, then we're guaranteed to have a point where the slope of the secant line is equal to the slope of the tangent line. So applications to the mean value theorem. The first one is a special case known as Rolle's theorem, a special case of mean value theorem. So Rolle's theorem states that the conditions for mean value theorem are met and that the average rate of change on the interval a to b is 0, then there must be a critical point x equals c on the interval. The idea being is if our average rate of change is equal to 0, then there has to be a point where our derivative is equal to 0 on the interval as well, as we can see from this diagram right here. Our secant line has a slope of 0 here, which guarantees since our function is continuous and differentiable over this interval, there have to be points where the slope of the tangent line is 0, satisfying the condition for a critical point. So applying the mean value theorem to an interval. The steps that we're going to use in order to carry out this procedure is a typical problem will typically ask you what is the value c such that the instantaneous rate of change is equal to average rate of change. So first thing you're going to do is determine an equation for your derivative, and then you're going to calculate the average rate of change over the interval for your function. If need be, because some problems do not require it, but if need be, you will verify that f is differentiable in the open interval, as differentiability implies continuity, so we can also check for continuity here. So if our function is differentiable, it's automatically going to be continuous over the closed interval. So as a result, we check for differentiability, and we don't have to worry about continuity since differentiability at a point guarantees continuity at that point, as we talked about in Unit 2. Next thing is we equate the derivative with the average rate of change, and we solve for x. Thought there was one more step after that. So let's take a look at an example right here. Find the value of x such that the instantaneous rate of change of the function f of x equals square root of x plus 6 is equal to the average rate of change over the closed interval -2 to 3. So if we have to check for differentiability in this case right here, all right, and continuity, we'll take the first derivative here. So first derivative, if we rewrite this in terms of a power function, is that we're going to have x plus 6 to 1/2 power. So the first derivative is going to be 1/2 x plus 6 to -1/2, or 1/2 square root of x plus 6. The average rate of change is going to be f of 3 minus f of -2 divided by 3 minus -2, which when we carry out the calculations will give us 1/5. Okay? So now we check for differentiability. We see that f prime of x is going to be non-existent for x plus a less than 0 or x less than -6. So f is differentiable over the interval of interest as no x values over the interval of interest are less than 6. AKA x is not differentiable for x less than -6 and no numbers less than -6 are on this interval if you're able to count. So now that differentiability is guaranteed, we set our derivative equal to our average rate of change. Okay, so we're going to have f prime of x equals 1/5, which means 1/2 square root of x plus 6 equals 1/5. Solving the resulting equation by using a little bit of algebra right here is going to yield that the value where the instantaneous rate of change is equal to average rate of change is x equals 1/4. And those are steps that we'll always carry out for such a scenario as this. A second example may ask, and this is really common on the free response section of the AP Calculus exam, is you'll typically be given a table and it'll show select values for a differentiable function f, and the part on the free response question will ask you, is it guaranteed that there exists a c over the interval such that f prime of c equals some value? In this case, some value is 0. So again, we check our conditions. We don't have to calculate any derivative here, because the problem is strictly asking for the existence of a certain derivative value. It's not asking us to solve for c, it's just asking, is it guaranteed that there's a point c where the derivative is equal to 0. So we can't calculate a derivative here, we're only looking for the existence of derivative, but we can calculate the average rate of change over our interval of interest, 0 to 4. So the average rate of change, f of 4 minus f of 0, divided by 4 minus 0, when you carry out the calculations, is going to be 7/4. So we know f is differentiable as it's stated in the prompt, so the mean value theorem can be applied. So by the mean value theorem, our first derivative is guaranteed to be equal to 7/4 at some point on an interval, but not 0. The reason being is that our average rate of change is non-zero, it's 7/4. If our average rate of change was equal to 0, that would guarantee that our first derivative has to equal 0 at some point. But because our average rate of change is not equal to 0, or not equal to the value of interest, we cannot guarantee that our first derivative will equal 0 over this interval. The only thing we can guarantee is that at some point our first derivative will be equal to 7/4. Okay? So in this last step, put more succinctly, you'll compare your average rate of change to the value that you're interested in, and if they match up, they're equal, your derivative will be guaranteed to be equal to that value. If the average rate of change does not equal the value specified, then it is not guaranteed that your first derivative equals the value specified in the prompt. And these are the applications of the mean value theorem.